So today I'm going to talk on one of my research topic. That one is impact of truck platooning on tool and rural highway in North America. Today, nowadays, actually, the most imminent and promising V2V technology is in the good movement industry is the semi or fully actuated truck platooning, which refers two or three trucks are connected together wirelessly. And the Society of Automotive Engineers proposed the driving automation from level 0 to level 5, where level 0 is indicating that human driver need to involve totally, and where in level 5 the human drivers in the platoon HCVs are replaced by the machine drivers. So and all of us also could see long combination vehicle in short we could say LCV are running on our roadways. According to Canadian Geometric Design Guideline, maximum 25-meter length of long combination vehicles are allowed to operate on our designated route. So now, because long combination vehicle and also truck platooning are quite similar in terms of length, and since the trucks in the automated vehicles will be controlled by a machine, so considering that fact, logistic industries are very much interested in the truck platooning. And from the research we have observed that when trucks are running as a platoon, they are the average fuel saving consumption could be 6 to 10%. And the driver shortage benefit, there is another driver shortage benefit. That one is in North America. Driver shortage is one of the key problem for the logistic industry. And one statistic shows that by 2028 in USA, they will require more 0.16 million truck driver, where in Canada we will require about 34,000 more truck driver by 2024. So that's actually a concern. So when we actually implement this truck platooning, we can get rid of this type of problem like the driver shortage, and can save some money by the fuel saving. There are several states in the world, some jurisdiction in North America specifically, such as California, Texas, Florida states in the US, and in Ontario province in Canada allows operating and testing truck platooning techniques along the designated multi-lane divided limited access highway only. Here you can see permitted highway section in Ontario for allowing truck platooning. The blue line is indicating where the testing are running. But if we want to get the full benefit of truck platooning, in that case, truck may need to travel through the two-lane rural highway. On the top picture, you could see that the normal condition when trucks are running and the passenger car, if the space they have get enough space, they could directly overtake the truck. But when two trucks are running, this is a concern. They may not able to have enough space. They may have to stuck behind the truck platoon. So this is a concern. So to estimate that, we have actually choose two objectives on this study. First objective is to estimate the appropriate passing side distance for truck platooning on North American two-lane rural highway using an analytical and simulation method, and compare the passing side distance, estimated passing side distance for truck platooning with the provided highway geometry design standard in the North America. So no other evidence we have identified which indicates the impact of passing side distance for truck platooning on the two-lane rural highway. Since none of the earlier model has touched upon the passing side distance for truck platooning, so to estimate the passing side distance for truck platooning, a new mathematical model has been proposed by modifying the Glannon mathematical model in our study. So here is you could see that where for the truck platooning we have considered WB20 trucks since WB20 is the maximum length single unit truck, so we have considered that. So based on that and based on the modified model, we have developed this analytical model. Here you could see the estimated passing side distance. The result showed that 2017, the top blue line are the tag passing side distance, and the bottom red line ASHTO geometric design, latest ASHTO, that means 2018 ASHTO geometric design guideline. I have to notify you guys from very beginning that the tag geometric design guideline, that is Canadian geometric design guideline, are similar with ASHTO 2004 geometric design guideline. After that, ASHTO has modified the passing side distance, required passing side distance, and they have the passing side distance is here. So from the result, what we have observed, the result showed that 2017 tag PSD is sufficient to allow car to overtake 2 or 3 track platooning on the two-lane rural highway. However, 2018 ASHTO is not sufficient to accommodate the minimum passing side distance for overtaking 2 or more ACV, more truck platooning, traveling in a platoon in the entire speed range. The results also indicate that passing side distance is almost 1.5 to 1.8 times more at 90 km/h speed than the 2018 ASHTO geometric design guideline. It's here. So the passing side distance estimated for track platooning, for a track platoon 3 CV platoon are much longer, like about 145-meter longer than those for overtaking a long combination vehicle. For an example, for the design speed 100 km/h. And 2017, from the analysis, we also see that 2017 passing side tag passing side distance provides sufficient passing side distance for the passenger vehicle to pass all 6 track combination options over the entire speed range from 50 to 130 km/h. And now there is a few more concerns. When the trucks are actually running on the two-lane rural highway, there are several factors play vital role, like opposing lane, traveling lane traffic volume, opposing lane traffic volume, driver behavior, vehicle acceleration, deceleration, speed, traffic composition, passing opportunities, etc. So these are the several vital rules. Vital factors actually play vital roles. So to develop this scenario, a micro simulation tool we have used, that one is Vissim. In this picture, you could see easily that 2 trucks are running as a platoon where the passenger vehicle are stuck in behind. And from this, from here, what you could see that a passenger vehicle is overtaking 2 trucks together. So based on this model, we have considered 3 scenarios, where first scenario was the higher traffic volumes, and the second scenario is a bit normal, and the third scenario is the lowest traffic combination. And these traffic combinations and the traffic volumes, everything we have taken from a corridor which are allowed, where long combination vehicles are allowed. Since long combination vehicle and the truck platooning are similar in comparison to in terms of the length, so we thought that okay, let's try with the long combination, where we have allowed long combination vehicle. So based on that, we have actually estimated the passing side distance for the truck platooning and also long combination vehicle. Here you could see the B train and double turn peak, where TD is indicating double turn peak long combination vehicle. In the simulation, from the simulation scenario, we could easily see that the results are not identical to the result obtained from the analytical approach. The result showed that clearly 2018 ASHTO passing side distance does not provide sufficient length for a passenger vehicle to overtake any of the 6 trucks option. where the 2017 tech passing side distance provides sufficient length for a passenger vehicle to pass the two long combination vehicle options and a good enough length for the passenger vehicle to pass two truck platoon, but it is well short of 85th percentile overtaking distance. Here the on the top you could see there is a orange line. This is showing us the 85th percentile. From here in the scenario 1 we could see that it's a bit short, but in scenario 2 and scenario 3, two truck platoon where the headway is 0.6 second, we could see that our passenger vehicle could able to overtake that truck platoon which are which are running with a 0.6 second headway. So what is the takeaway from this analysis? The analytical and simulation analysis suggests us many existing two-lane rural highway designated in accordance with the passing side distance requirement in the 2004 ASHTO passing side distance or 2017 tech geometric design guideline could be used for track platooning operation, and two track platooning may be feasible for two-lane rural highway, but that need to meet the 2004 ASHTO or 2017 tag geometric design guideline. But we suggest providing a frequent passing lane for highway sections designated for two track platooning would reduce possible safety concerns. And here are the reference what I have used for this research. And I would like to also thank Smart Face Center for funding this research project, and IT York University student chapter, as well as PTV group for supporting me to conduct this research.
So welcome you all to my presentation. Thanks for being here today. But today I'm going to present one of my research work that I have been doing and recently been accepted for TRR journal, the effects of connectivity and traffic observability on an adaptive traffic signal control system. I'm Aslam Ebin Al Islam. I'm a PhD candidate from North Carolina State University. I'd like to thank my co-authors, Mehrdad and Rasul, and my advisor, Dr. Ali Hajbabai, for their support to finish these projects to research. So without further ado, let's move to main presentation. So the effectiveness of the adaptive signal control system not only depends on how well the control algorithm designed, but also it depends on the ability of the control system to observe the traffic condition, which is actually dependent on the quality of the traffic data it collected. So overall, that means the effectiveness of the adaptive signal control system depends on the quality of the traffic data. The good news is the emergence of connected vehicle technology, where vehicle can share their real-time, reliable traffic data to the signal controller, help us to observe the traffic systems quite efficiently. But there's a bad news too. The bad news is the current penetration rate of the connected vehicles are very low, and it shows that it requires a significant portions of the vehicles to be connected to get a very good estimation on the traffic observability. So you will find a lots of study that integrates secondary sources of data like loop detector data, historical data with the connected vehicle data to compensate for the limited data in low penetration rate of CVs. So there is always a question, what is the best time to transitioning from a detector-based signal control system to CV-based signal control system? So in this research, we try to find a timeline in terms of connected vehicle penetration rate by quantifying the effects of traffic observability on the mobility performance, traffic progression, and travel time reliability, both in vehicle class level and the direction level in an arterial. So this research will use one of the signal control algorithm that actually handles different sources of data. That means the CV data, it can handle only CV data, only loop detector data, or by integration of the both CV and loop detector data. Then we'll test it for different CV penetration rate We analyze their delay, travel times, volume to capacity ratio, and distributions of travel time, and finally try to figure out what is the effect of the observability. So here in this simple graph is showing this when the CV penetration increases, how the observability depends for different data sources that is available in the traffic network. So when the signal controller only use CV data, with the increasing penetration rate, it increase the number of vehicles that are connected, increase the availability of the signal controllers to see the where the vehicles in the network. But when the loop detector, we use only the loop detector data, no matter what the penetration rate is, the observability is always same, because it actually detects the vehicle whenever a vehicle goes over it, no matter if it is connected or unconnected vehicle. And when we integrate both the CV and loop detector data, we find a better observability, which is from the very beginning better than the loop detector data. And finally, this is our goal, to find these 2 points, which is the critical penetration rate we defined as the penetration rate that only CV-based signal controller system requires to outperform the loop detector-based performance of the loop detector-based controller system. And finally, another point where we don't need any more integration of the loop detector data, both the signal controller system, when only use CV data or integration of CV and loop detector data, gives us the pretty much same results. So in that case, in this point, we can get rid of having dependent on the loop detector data. So this is our whole goal for these projects. And let me tell you how the signal control system designed here, how the different sources of data is managed. So in this simple two intersections network, we shows that vehicles that are connected, that can actually share their speed, accelerations, and positions once 10 times a second to the roadside unit, and these transit bus also can share their intended phase to the roadside unit. So when all the vehicles are connected, that means when all the shares their information, the signal controller itself know where all of these vehicles are. It can actually get a very good idea about the traffic condition around the intersection. But the problem when there is no enough connected vehicles. So some source of some vehicles shares their information, but pretty much not all the vehicles shares their information. In such cases, we use the detector data to compensate for the limited data availability and low penetration rate of CV. So here's how we do it. So I'm showing a very simple cases of one into a single lane. So here's a detector here. So all the blue vehicles are CV vehicles, and red ones are UV, that means unconnected vehicles. So all the points here you are seeing is the sample of the CV data that are collected. And here in the place of detectors, you see the detections of the vehicle. So if we closely look at these, the CV data and the detector data together, you will see there are some places where there is only detections collected, and there are some places where both the CV data and detections are collected together. So that means when the CV and detections, CV data and detection data both are collected, that means that's an entry of CV, connected vehicles. And when only the detections is collected, that means it's an entry of UV, it's not CV. So now we use this information further to find out what will be the locations of the unconnected vehicles over the network. So here in this one, in this time space diagram, if we focus in certain part at any time, so these vehicles, in this one here it is showing the detections of the detectors. So we can find the arrival distributions of the vehicle, and more importantly, we can find the arrival distributions of connected vehicles and unconnected vehicles. And at any time, these are the positions of the vehicles over the link that we are interested to find the positions of the unconnected vehicles. So you will see these connected vehicles shares their information. So signal controller know exactly where they are. The problem is for these unconnected vehicles. To find the positions of these unconnected vehicles, we assume that distributions of the vehicle positions over link is actually equivalent to the arrival distributions to arrival to distribution that is collected from the detector data. So once we have these, we know we can transfer all those information and find out the places of all the vehicles, even though we are in a low penetration rate, even though some of the vehicles don't share that information. So then the signal controllers use those information as an input and optimize the traffic signals. The traffic signals try to minimize the passenger travel times for all the vehicles and prioritize the movement of the transit vehicles, and find the feasible traffic signals. That means feasible means it should find the signals that is non-conflicting, where the vehicle can move the conflicting area without any conflict with other directions. So once we have all of these, it optimizes the signals and then sends it to the controller, and controller implement it on a rolling horizon basis. So by rolling horizon basis means it, when it collects the data, it plans for a certain period, for example 1 minute, and it tries to find out what will be the conditions of the network in next 1 minute, and based on that it optimize the signals, but implement for few seconds, for example 2 seconds, 1 second, 5 seconds. So that actually helps the signal controller to adapt with the stochasticity in the network. Transportation network is so stochastic, and also, as I said earlier, the adaptive signal control depends on how effectively it can capture all of these conditions. So rolling horizon basis actually help us to get a real-time solution, also helps us to adapt with the uncertainty in the network. So once we have the signal controller get all of these informations, and then they shares the informations with the adjacent intersections controller, so that the number of vehicles are going to come in the next few seconds, that can be estimated based on the data shared from the adjacent intersection. So each of these intersections has a broader overlook about the network traffic and signal control system that it can find not only good for itself but also for the entire network. So I just wanted to show you a simple animation of how the adaptive traffic signal control systems can outperform the conventional transit signal priority based system in 100% CB penetration rate. So these two animation is showing that. In the left one, we are showing the performance of the total bus delay, and right one is car delay for both the transit signal priority and adaptive signal control system. So you'll see over time how the adaptive traffic signal control systems actually provides the better results for both the bus and car in terms of their delay. So once we have that, now let me just introduce with the case study that we used in this study. We had 10 intersection network, which is in Washington, SR 522. We get the data from Washington State Department of Transportation. So about the volume, bus routes and everything. So there are 7 bus routes there. We have their headways, and you will see the volume, peak hour volume that we use. Definitely it has a higher volume in the major direction than minor direction. So then let me just show you how we have implemented this one in the vSIM simulation. So we use the vSIM com interface and coded the entire program in Java, and we use a multi-threading system for as an architecture for this work. So in the vSIM simulations, we collect all the data from the CVs and the detectors. CV provides us the basic safety message. We use the traffic state estimation algorithm. That means integration of both of these basic safety messages and detector data to find out the traffic state for the entire network. Once we have all of these, each of these intersections, the data corresponding to each intersection provides to each thread, and then each thread use Cplex using the multi-threading architecture in Java. Use Cplex to optimize the signal. So once they optimize the signal, we provide this We implemented the optimized signal through COM interface in the main network that we have, and finally we ensure that each of these information optimized signal controls are shared between adjacent intersection in the multi-thread environment. So here are the three strategies that we used from two data sources. As I said, one use only loop detector data, so no matter what's the penetration rate of CVs, and then we use the only available CV data to estimate the traffic state. So the signal controllers only use the CV, and finally that it integrates CV and detector data to provides more observability in the system. So here's the result. At first, I will show the mobility performance result for passenger cars. Here in the x-axis, we are showing the different penetration rates of CV and the average car travel time for entire network, major direction and minor direction for different sources of data. The loop detectors only loop detectors in CV data and CV data. So you will see a 30% penetration rate for the entire network. And the passenger car, it requires 30% penetration rate of CV to outperform the existing loop detector-based signal control system. Similarly, for the major direction, it requires 40% and minor direction 30%. Most importantly, if you see around 50%, after 50%, the performance with both CV data and CV and loop detector data are almost very similar. So at this point, when we reach the 50% CV penetration rate, we can rely only on CV data. We don't need to integrate loop detector data if we want to find the better mobility, optimal mobility performance for the entire network. Here is the transit bus. So it shows the similar trends, but requires a less penetration rate, like 30% penetration rate. So one of the main reasons is that it has a lower volume, and most importantly, they are connected. So even though we have low penetration of connected vehicles like passenger cars, but the transit vehicles were always connected throughout the case studies. So it requires only 30% penetration rate to provide a better average bus travel time than compared to the loop detector based solution. So, and then in the major directions show the same, and around 50% penetration rate, the both the CV data and CV and loop detector data shows that similar performance. But in the minor direction, we didn't find any important trend, because most of the cases, the vehicles travels along transit vehicles travels along the major direction, major arterial. There is a very low amount of transit volume in the minor direction that didn't capture actually the actual trend there. So, and for travel time reliability, when we use only the CV data, we show the cumulative probability distributions of the travel time for different penetration rates for loop detector data and other penetration rate, both for passenger car and transit vehicles. So you will see the red line here is actually showing the travel time CDF for the loop detectors only. So it shows that it requires only 40% penetration rate if we just use the CV data for the passenger cars, but for the transit vehicles, it requires 20% penetration rate. So it's the explanation is similar. Even in low penetration rate, the transit vehicles is always connected. So, and when we integrate the CV data with the loop detector data, it can actually outperform at the very beginning, like at the 0% penetration rate, it has the better results compared to the loop detector solution for both passenger car and transit vehicles. And here it shows the signal progressions quality. I'll show for two intersection, 1 and 2 intersection for both directions. So we have seen for different penetration rate, we are showing percentages of percentage of green ratio and vehicle to capacity ratio. So for entire penetration rate, the signal control systems that we have is actually for different data sources maintains the undersaturated condition with without significantly increase the length of the queue. So at the result, we have seen that the 40% penetration is required when you use only CV data to yield a better mobility performance than using the loop detector based signal control systems. And CV can actually consider around 30% penetration rate if it wants to have a better results, better performance than the loop detector based signal control system. Around 30 or 40% penetration is the optimal one. And after 50% reserve, 50% penetration rate of CVs, there is very marginal gain of integrating loop detector data with CV data. So this concludes my presentation. Thank you all for being here.